With this lesson, we are going to get started working with the properties of kites and trapezoids. We've already seen throughout our quadrilateral unit that we've spent a lot of time working with parallelograms, and we saw that when you have two sets of opposite sides that are parallel, it has a whole lot of things that are caused to be true. Well, kites and trapezoids do not have these two pairs of opposite parallel sides, and so when we lose that criteria of having two sets of parallels, what other things will pop up? Our objectives are, of course, to start taking these properties of kites and to take the properties of trapezoids, especially isosceles trapezoids, and use them to start solving problems and answering questions. And so, of course, we have to start off with what the shapes are themselves. This is a kite. I'm sure that you remember a parallelogram will have two pairs of opposite sides that are congruent. And we actually use this picture as a criteria to show that we actually need them to be opposite. If we have two pairs that are just congruent without being opposite, we get the kite shape. Now, there's one really immediate and simple observation that you should make with the kite. If we draw in this diagonal, you should instantly see that this sets up side, side, side. So we know in a kite, this top and bottom triangle are going to be congruent to each other. Additionally, if we draw in the second diagonal, or before I get in there, well, because these two triangles are congruent, you'll notice, of course, that we've got one pair of opposite sides that are congruent. We also have this diagonal would bisect the two angles on the end, just setting up our matching pieces. That's what some of the properties are. You're supposed to recognize that we have these angles that match up. Additionally, if we draw on the second diagonal, what does it look like we've got going on with the angles in the middle? They look like a bunch of 90s, and in fact, that's true. They will all be perpendicular to each other. Having these sets up a massive amount of congruent triangles. When we look at these pieces, of course, we've got top and bottom. Those triangles in the purple will be congruent. And we can set it up so that we would have, I want this in yellow, these two medium-sized triangles would be congruent. And we already saw that we had the overall big triangles being congruent, but there's a lot of matching parts. And as we've seen with congruent triangles, matching parts means that we're going to get a lot of things congruent. And that's all that our two theorems are telling us. Our two properties for kites are simply telling us that we will have the diagonals perpendicular to each other, creating a large number of right triangles. And also, because of the diagonal creating top and bottom congruent triangles, we have an opposite pair of congruent angles. So, to use those, let's answer a question. Measure of angle DAB, D to A to B, that's 54 degrees. And we would have the measure of angle CDF, CDF is 52 degrees. We are asked to figure out the measure of angle BCD. So B to C to D, that's what we're being asked to get. And it's worth noting there is a lot of information that we can get out of this. There is more than one way that we can reach this answer. The first thing that I think about, though, we've got these 90s in the middle. Let's take advantage of the fact that we've got all these 90-degree angles. When I look at the picture, I see this triangle right here. we were given this is a 52-degree angle. And we know the center gives us a 90. What do the angles of a triangle always add up to? Add up to 180. And we know that we've got 52. We know that we've got 90. Those two things added up will give you 142 degrees. And when we subtract 142 off of 180, that tells us we have 38 degrees. So this little chunk here now, we know is 38 degrees. But because of the congruent angles, we know that the top and the bottom are going to be the same. So the top is 38. And of course, the angle we wanted to know just there. It's just 38 times 2, giving you 76. We're done. It's really, really common when you're working with kites, because we've got these 90s in the center, it's really, really common for you to use triangle sum 180, given the fact that you already know one of them is 90. Also, because the diagonals chop the kite up into 4 right angles, using the Pythagorean theorem is massively common when you start talking about side lengths on these problems. This is still another angle problem though. PQR is 78. And right away I'm going to stop and say, I know that I could cut 78 in half. 78 divided by 2 would equal 39. And so I know both of these pieces here have to be 39s. Continuing further, we have angle TRS. T, on green there. Erase that. T, come on. Green. TRS. That one is 59 degrees. Again, keep in mind, we've got congruent triangles. The fact that this one is 59 tells me its congruent counterpart, its corresponding one, is also 59. And now we need to know how big is QPS. Well, of course, we can see that we need to figure out this little chunk. That's not a problem, though, because, again, we've got this right triangle up the middle. 90 plus 39 gives us 129 from that 90. And when we subtract off 129, we get 51. So this piece in the red is 51 degrees. The piece in the green is 59. We can put those two together, getting the angle we were looking for, 110. When you work with these pieces, you are going to use congruent triangles all over the place because you've got 3 different pairs of congruent angles. And we haven't done anything here with side lengths, but expect to see the Pythagorean theorem because every single triangle is a part of a right triangle, so all of them can use Pythagorean theorem to figure out all of those chunks. Second shape that we need to work with is a trapezoid. Trapezoids have exactly 1 pair of parallel sides. Usually the way you draw them are top and bottom are parallel, but of course we know that they can be slanted or rotated, flipped, whatever. When we work with a trapezoid, we've got the base and base, top and bottom bases as well as the base angles. The two non-parallel sides are called legs. And where these play a significant role for us are when we work with isosceles trapezoids. I'm sure you remember when we talked about isosceles triangles, it meant that two sides were the same. In particular, the two legs were the same. It's the same thing here. An isosceles trapezoid has two legs that are the same, and so I want to show you a couple things that are true about isosceles trapezoids. And here's where I really want to emphasize something. Every single thing we're looking at here is about isosceles trapezoids. And so when we look at these, please notice that this is saying we're starting by knowing that it's isosceles, so we have two sides that are the same. And this theorem tells us it actually forces your base angles to be equal in size, and that's going to cause the top angles to be equal in size. Essentially, two matching sides forces two matching angles. And it works in reverse. If you knew that you had the base angles being the same, two matching angles works in reverse and forces two matching sides. But it doesn't stop with just angles and sides. It's also the diagonals. Two matching sides will take and force your two diagonals to be the same length. Or in reverse. Two diagonals equal forces two sides equal. Basically, this theorem is saying it's all interchangeable. Two sides, two angles, two diagonals. If you get any one of those three, you get the others for free. And of course, where this plays a role is just looking at a problem like this. How big is angle F? Pretty quick. This is isosceles, which means our base angles match. But don't forget that we do have a set of parallels, and with a set of parallels, we have same side interior. Same side interior have to be supplementary. When you look at this problem, all we're recognizing, the only thing we need to see is, because this is a 49, we've just got a simple piece of subtraction. Done. It's 131 degrees. Another problem. When we look at it, you should see the tick marks, which tell us two sides are the same. Those tell us then that the two diagonals are the same. They have to be the same length. So when we start putting in our information, JN is 10.6, NL is 14.8. Obviously, we can take those two things, put them together using the segment addition postulate. And so we get the red diagonal, 25.4. But since it's isosceles, the diagonals are the same, so the other diagonal, KM, is also 25.4. Done. That's it. The problems are just built on the idea that we can switch back and forth between matching number of sides, matching number of angles, matching number of diagonals. What about here? What relationship would we have? Again, let's pay attention and see. How big should A be what should the value of A be so that we have an isosceles triangle, an isosceles trapezoid? Well, in order for it to be isosceles, two sides have to be the same, which means that we have to have two angles the same, or base angles. We need those two angles to be the same size. Therefore, all we're doing is saying 2a squared minus 54. We need it to be equal to a squared plus 27. And when this is true, when we find the value of a that makes it true, that forces two angles, the base angles, to be the same, which forces it to be an isosceles triangle. So solve the equation. We can subtract off a squared from both sides. Of course, 2a subtract 1a leads us to just a single set of that a squared. We could add 54, giving us a squared equals 81. After taking our square root, we have our solution of 9. Done. Built entirely on the observation that this causes the angles, which causes the sides, which causes it to be isosceles. One last piece of information that you should know about trapezoids. Last term, we saw that we could have a triangle, and we had the mid-segment of a triangle. In particular, that chopped the left-hand side at the midpoint, it chopped the right-hand side at the midpoint, and the characteristic that we had here, if we had our base and we wanted to know the length of the mid-segment, just cut it in half. Well, this top we could kind of think of as a trapezoid with a top length of 0. When we look at this mid-segment, if we were to start shortening it up, or the trapezoid, and start shortening it up, shortening it up, shortening it up, eventually, if we chop off this whole other side, we would be left with a triangle. And so, essentially, what we're thinking of is a trapezoid is a triangle, or rather, I said that backwards. A triangle is basically a trapezoid where the top base is 0. And I'd like to make the observation that this base, the midsegment of 5, is halfway between 0 and 10. That halfway relationship is still going to carry through with the midsegment. If we had a top base of 10 and a bottom base of 20, the midsegment is going to be halfway between those two bases. It would be 15. And so we wind up having this theorem that goes through and explains all this, but basically the midsegment just has the relationship that the midsegment is halfway between the top and the bottom base. You just add the two bases together. In the previous example, 10 plus 20 would have given us 30. Cut it in half. Half of 30 is 15. This equation governs the relationship of putting the midsegment halfway between the top and the bottom base. And so our last example then, how big is this midsegment? And of course, these numbers aren't as easy as 10 and 20. If you've got easy numbers like 10 and 20, go ahead and go halfway through, but it's not as easy to say what number is halfway between 8 and 13.5. Which is why we would take these two things, add them up, giving us 21.5, and then we just have to take half of 21.5, which gives us 10.75. That's how big this base would be. And I just wrote 2.5 there, 10.75. And so there, we're done. All our properties that you're expected to pick up on, you should know this relationship for the mid-segment of a trapezoid. You should know that isosceles trapezoids are almost interchangeable with number of sides that are the same, number of angles that are the same, number of diagonals that are the same. If you get one pair of the same, it causes the others to be as well. And when we're working with kites, we will have a boatload of right triangles. And so we'll use sum 180. We will use congruent matching triangles. We will use Pythagorean theorem. And that's really all that we need to know so that we can accomplish our objectives of solving problems about both kites and trapezoids.